questions later. Maybe we should start. Are you guys all seeing? Am I muted? Are you guys all seeing? Oh my God. All right.
Oh wait, turn on the video.
There we go. Guys, look at our new feature, our very cool background. Okay, anyways. So welcome to ACMA AI Presents Optimizations, where we're gonna teach you how to optimize your neural networks. So we're gonna start with a Kahoot. Oh, Kahoot, yay. All right, let me stop sharing. Enjoy my memes first. All right, now that you guys have enjoyed my memes, I'm gonna stop sharing and share the Kahoot. How do I start this Kahoot? Share screen. Does this work? All right, who's Benjamin Dover? Who's Bob Joe Car? All right. What the heck? How many people is this? 22. We're missing like 12 people. Oh, gradient ascent. Let's go.
Can you guys still hear audio or no? Edward, are you able to hear audio?
Oh, people can't hear anymore.
You can or you can't?
Cannot.
Okay, let me redo this. Let me reshare. How about now?
Turn down the sound. It's too loud. It's too
How
loud.
do I turn it down? I don't know how to turn it down. All right, too bad. We're starting. Last call in 3, 2, 1. If you win, you get 10 Edward bucks.
What is this? This is how you play the
Remember, the audio settings in the top right. Or does that turn off?
I don't know how to
Maybe
turn the
we don't
audio
know.
down. I'm
Check
sorry.
the codes from our membership portal at members.acmucsc.com. So
Oh,
make an
top
account
right.
there and you register.
Top right? What is he saying? Top right?
No, it's on the top right of this. Wait, give me a movement access.
Give you what?
I'll do it for you. Yeah. What? Okay, wait. Okay, I'll do it for you. Wait, the thing disappeared. Click on the thingy.
Where?
Do you see it? I think I mouse on it.
I can't technology.
Wait, it's not letting me click anything. It is.
Top right.
No, wait, it's literally there. Like,
See, this is why you should have shared, Edward. All right. Oh, is it one of the?
you see the button right on top of skip?
Right on top of what?
On top of skip?
I can't can't hear you. It's too loud. Can you type what you're trying to say in chat? Oh, I see it. Adjust volume. There we go. Did that work? Let's go.
What the heck?
Is it too soft now? Ooh, A is now in first place. How cool. Bajo Carl in third. Oh, okay, I got you with the commentary. What is backpropagation? There are 4 very good answers. I can't tell which one is correct. I'm kidding. Of course I know which one's correct. Woo. Next. A is still in first place with 1 digit away from the best number. It's the clothes that neural networks wear.
Oh, but did you just advertise all the Spice Kids?
Advertise what?
Did you advertise all the Spice Kids?
No. Who are we? No. 5596. A is still in first place. All right, Edward, take over the commentary. Thanks.
Okay, fine. So, what is a node, neuron, perceptron in a neural network? A, the things that make your brain work, and like the rest of them. Yeah, it was C.
Why are we talking about biology? Who put that? I'm kidding. Don't expose yourself. All right, let's see if anyone gets to 6666 next.
Which of the following is not a type of neural network layer? Thick layer. It's a thick layer. Okay, technically it's not called a hidden layer, but it is fine. A hidden layer is a general term.
Thanks for the clarification, Edward.
Why do we need to find the gradient of velocity?
It's yellow.
Yeah, I think it's blue.
Someone put yellow. All right. A is
Wait,
still in first place.
A is popping off.
Exactly. All
Who's it?
right. Let's go. All right, guys, there's only one correct answer. Oh, well, Kahoot has spoken.
I feel bad. Oh,
Bajo Carl in first place. By the way, that is not me. Bajo Carl is not me. I don't know.
Roger Carl's. Wait, Catherine, is it time for me to draw the YouTube link?
Why is it so wrong?
Oh, how unfortunate. Let's see who won. All right, Bajo Carl, bring me honor. Was?
What? That's insane.
Bajo Carl 2. Rock.
Is that Jason? I feel like
Is
it's
it?
Jason.
All right.
Jason's not here.
I think we can make
That was
it
fun.
harder.
If you're one of these top 3 and you want clout, you can say that was me in chat, and Edward will congratulate you. I'm Bajo Carl too. Oh, congratulations! All right, I'm gonna stop sharing. Edward, you want to share the slides because I feel like screen sharing is kind of hard.
No, you can screen share.
Are you
Wait, no,
serious?
my computer's literally like kind of slow right now. I'm trying to do something right now.
Okay, fine.
Congratulations, Dennis.
Let's see. Now all right, back to the actual thing where split. Is this correct? Your screen is paused. Can you guys see this?
Yeah.
Okay, we'll be continuing now. Poll question.
Wait, no, go to the one before that.
Oh, agenda. All right, Edward, you want to take this?
Okay, so first of all, we're just going to go over the agenda of today's workshop. The first thing we're going to do is talk about what can we do to make a better neural network from last workshop. And then after that, we're going to talk about underfitting and overfitting and like how to like recognize if you're overfitting or underfitting on the data. And then afterwards, we're going to talk about hyperparameters and also regularization and lambda parameters. And at the end, we're going to talk about weight initialization and different optimizers. And there's going to be like a lot of memes. Yeah, next slide, please.
All right, next slide. This is so complicated. Okay, so we're gonna have a poll question. So how can we, let me just.
I just pulled it.
Oh, nice, thank you. How can we improve last workshop's neural networks?
So A, feature engineer our data. B, make our model more generalizable. C, improve the prediction accuracy. D, choose better hyperparameters. E, all of the above. Or F, you can't. Our last workshop neural networks are better than Google's.
All right, let's wait for a few more people and then I will share the results.
50% of you guys have confidence in our skills to beat Google.
All right, Stone, you can end poll whenever you want.
Okay, we're gonna end in 3, 2, 1. Wait. Share results. Yes, so answer is E, all above. All of those are methods for improving neural networks. And yeah, we're not that good. AI is really hard.
That is true. That is a good point. All right.
Next slide. So I'm going to talk a bit about first the concept of underfitting and overfit. The concept is that when you're training a model, how do we decide if it's good or not? One of the best things we want to know about a neural network model is how good is it at predicting data and how good is it at predicting unseen data. So in this graph, we'll show you the concept of underfitting and overfitting. Underfitting is when your model is too weak and it can't predict data well. So you'll see in the data on the left, it's underfitting because it's like trying to predict its decision boundary between red dots and green dots, but it clearly is failing. But if you do overfit, say you're running some very, very giant neural network or some high degree of polynomial function, more often than not, you're gonna have a perfect match and a perfect decision split of your test data, the data you train on. But the problem is when you add in new data into the data set, you'll probably predict them all incorrectly. And the last thing is what you want. You want to balance between underfit and overfit, which is at which point you have good generalization of your model. And with good generalization, this means our model will perform better in the real world instead of just the test data. So the first thing we're going to talk about is how do we get these graphs? How do we know what is the typical way of training our models? So something we didn't mention last time is the train test split. Typically in data science and machine learning, we often split our data into a ratio of 80 to 20 for training and testing data. So given a data set, we'll slice the first 80%, keep it as training, slice the last 20% and keep it as test data. We use our training data and we train on it. And what we do is we estimate the true model performance using testing data. So what I mean by true model performance is basically like how well does it generalize? How well does the model perform on unseen data? Because remember, using our optimizers, we know mathematically that we can guarantee our neural network can find a good local minimum for the training data. But for the test data, it's a completely different field of data. So like the local minimum there is different. So we want to be able to have good performance on test data or unseen data. And obviously, if a model has lower cost on training data than testing data early on, we're likely to have overfit on our training data. So what's one thing we can often do is when you're training your algorithm, at least in TensorFlow, I'll show you guys, you see a loss and a validation loss or a test loss. When you see your loss on your training data set is very small, that means you've kind of overfit on your training data. It means like you can predict almost everything in your training data correctly. But if your test data set's error is not going down, that means you're not generalizing. And if a model has in general high cost and poor accuracy, we're likely to have underfit on our training data. In our case, cost and accuracy are synonymous terms. We want to lower our cost, which is basically the same as increasing our accuracy. And we basically use this result of this comparison between our training loss and our test loss or accuracy to tune our hyperparameters, which include anything but the weights and biases. So such as number of layers, type of activations, number of neurons per layer, etc. Now the last thing I'm gonna show, go next slide. Next slide. Wait, don't click next. So now just another thing. Now what's actually more commonly done is we usually have a training, validation, and test split. So this is slightly different. We have 3 splits now instead of 2. Can you guys kind of guess as to why you might have a 3-way split? Because there's actually one vital flaw to the previous slide when we're doing a training test split. Next slide. So the idea here is that when we're on a previous method, when we do a train test split, we're tuning our hyperparameters based on our test set. But that means our test data now is become biased. It's biased to our own intuition about what hyperparameters work. So that's why we have 3 test splits. A training data, as usual, and now we have a validation and a test set. The validation set is what we use to tune our hyperparameters, and this allows our test data set to remain untouched and unobserved. So this reduces our bias and gives us a much more accurate estimator of the true performance of our model. And sometimes you might want to adjust this 60-20-20-20 ratio, which is a typical ratio, depending on what you're doing. So for example, for models, some more complicated models might require more training data to generalize and learn, so you might want to increase the ratio, or you might want to decrease it if you don't need that much training data or something. Next slide. So here's the last thing about underfitting and overfitting, and how we can address this between using some different ways to address this, from train test split, train validation test split, and k-fold cross-validation, our final method. For k-fold cross-validation, this is more complicated, but it's also commonly used. This is very useful when data is limited, because when we call in our test splits, our data splits, what we're doing is we're kind of throwing away data that we could be used to train our model. So what we do instead is with k-fold cross-validation, we choose a number k, we split our data set into k sections, k groups, and from iteration 1 to k, we choose a kth group of data as our validation data, and the rest is used for training. And then the average of validation scores kind of just serve as a performance metric. Slides I'll post in Zoom real quick. Wait, go back. Oh, let me also drop the checking code again, because if you guys weren't here, we did our Kahoot. Oops, that's wrong. Yeah, any questions about k-fold cross-validation, train, validation test splits, just data splitting, and why we do that? And just to reiterate, these data splits, and the k-fold cross-validation is used to address the issue of hyperparameter tuning. We want to use these methods to help us tune our parameters based on how well the model performs on validation test sets or data sets. What are these names? Okay. Yeah, let's move on. Here we have our next poll question. So now we're going to talk about overfitting. How do we fix this? Because this is probably one of the most common issues with neural networks usually. Usually you can easily make a giant neural network, and the bigger neural networks typically can model your data much better and much more easily given enough time. But the issue is if you fit to our data too closely, it won't generalize to unseen data. So the question is now, which of these methods may help make our model more generalizable and less overfitting? I see Edward smiling now. What are you doing?
Nothing.
Okay.
All right, I'm gonna end the poll in 3, 2, 1.
All right, yeah, so some of these are right. A, C, and D. So using more layers of neurons is not right, because if you guys recall, using more layers of neurons actually allows us to model much more complicated functions with as many parameters as you want. Using non-convex, super complicated activation functions also doesn't simplify a model. Just recall, it's like the one rule of thumb is just like the more simple your model, the less likely you're to overfit. So that's why you want to use less features, maybe less layers of neurons. And the last thing E will bring up to later, and we'll talk when we talk about regularization. So next slide. So here's a nice meme from Alvin.
This was Edward.
So usually to address overfitting, these are known as regularization techniques. Just recall that more neurons and layers equals a much more complex model, and it's actually more easy to overfit things. So how do you know when your model is overfitted? So one way to tell is when you plot the loss curves. So when you're training your model, you have a plot of like the loss, right? Your loss score over time. And then you also have a loss score on your test data set or your validation data sets. If your validation data set's loss score is much higher than your training data sets, that means your model doesn't generalize. That means on unseen data, on unseen validation data, it doesn't know what's doing. It's doing the wrong thing. But if those two loss curves are similar, or at least over time they reach about similar and converge to the same value, that means you've generalized pretty well. Yeah, so less neurons and layers equals a much less complex model. And if you guys know the saying, this is Occam's razor. The simple model is more likely the right answer as well. Well, we have a less complex model is actually more likely to underfit, but this is a really hard thing to balance. So one way to address overfitting is to employ various regularization techniques. We will introduce one today. There'll be more to come in the next workshops using techniques such as dropout layers. Another idea is using less features. So as an example, let's say we have data on Boston house pricing from front yard area, floor count, bed count, bathroom count, number of dog houses, I don't know. When we have more features, one, it makes our model train slower. Two, our model might learn correlations or spurious correlations, sorry, that don't work for unseen data, but it just so happens that the data set we have is biased to one data for example. For example, let's say we have this Boston house pricing data, and let's say there's a column called number of dog houses. And let's just say it just so happens in this one area of Boston, the more dog houses you have, the more pricey your house is. But in the rest of Boston, it's actually really random. So when we're training our model on something like this feature, it's going to be biased to the dog houses feature, and this will cause it to overfit. Because we know that on unseen data where dog houses is not as influential, it's just not going to work. And there's another thing, this is more complicated that we're not going to be covering in this scope, but it's basically just math. It's a concept known as PCA, Principal Component Analysis. This effectively reduces the number of features to a subset of data with higher information efficiency. So think about in a 3D plane, you have a lot of points, but it could just be that all those points are actually just on the same plane in the 3D space. So really the only thing we need to know about these points is that they're all in the same plane instead of just knowing that they're in 3D space. So not only does PCA actually make your model train faster, which means you get better results, higher development speed, allow you to iterate more. It also allows you to use less features, which will mean you're less likely to overfit. Any questions? Are there better dimensional reduction techniques beyond PCA? For example, for classification, finding the subspace with highest between class variance to within class variance will produce a subspace that is better for distinguishing between classes as opposed to just maximizing variance of data. I'm gonna try to process this real quick. PCA is pretty standard. You can't really go wrong with it. Although the only thing you need to be wary is that another thing in PCA is you repeated a variable K, which is the dimension you want to reduce your current feature set down to. Can anyone answer David's question? I don't think I quite understand. I do agree though, PCA is not the only method. There are definitely other methods as well. Yeah, PCA is a very general technique. For every single AI field, there's different techniques for reducing the dimensionality, especially computer vision. All right, next slide. So I'm gonna cover a bit of the math for one specific technique known as regularization. We're gonna call the one we're introducing today is called L2 regularization. It's also known as wave decay. So this is very simple. In our loss function, any loss function, all we do is just add what's called a regularization term. Lambda over 2n, n being the number of samples, and sigma for every single weight in our model, we take the sum of all of them squared. So what this does in our loss function is effectively is that we penalize large weights. If the weight is large in a model, it's going to increase our loss function. So we want to penalize that. The intuition behind this is that we want our model to be concise, compact, and we only ever want to make big changes to weights if and only if they cause a greater decrease in loss. So here's an example of regularized mean square error. As you guys may recall from last workshop, our mean square error function is just 1/2n, sum from 1 to big N, the number of samples, taking the difference of our prediction and the true label or the true value and squaring it, taking the norm. So what we're basically saying is that our model should only update the weights in a certain direction, given that the original loss function decreases a lot more. So what this does is that by making our model simpler, this is going back to the idea of making our model simpler. It just means our models can be concise and less wacky with crazy high, probably wrong weights. Anyone have any questions about this part? All right, cool. Next slide. Wait, one sec. Okay. Someone just asked. No, so actually in particular, sorry, I forgot to explain this. L2 regularization is using W squared. L1 regularization is using just W, just the absolute value of the weight, or the norm, sorry, the norm of the weight. But yes, for L2 regularization, for any regularization, you always add that much to the loss function. So larger network equals higher loss. You could say that, yeah. Maybe initially, it'll start off of a higher loss, the larger the network you have. But in the end, for a larger network, it's going to try to learn smaller weights for each neuron. So to make each neuron, make it like a smaller cog in a bigger machine. It's basically using a true norm, yeah, L2 norm. There's also something called L2, L1 combined regularization. If you see our TensorFlow code, you can see that it's actually one of the options, but we're not explaining that today. All right, next slide. So yeah, there's also a lot of other regularization methods. Literally each step of the data science process and ML process can be changed to help reduce overfitting. As an example, more diversified data collection. For example, let's look back at our Boston housing price data. If we had better diversity in the kind of housing prices data from all over Boston, instead of just that one area where dog houses were a core feature, we would have less overfitting on that feature. This is something very new. I only found out like recently. Crowdsourced ML is a new thing now. There's a thing from Stanford called Flock, where what they do is they get people to pick features, to pick a model using crowdsourcing, like I think Amazon Mechanical Turk. And then apparently it's more likely to reduce overfitting for some tasks. There's also special layers, which we will get to next workshop, which include dropout and a lot of other ones. And yeah, there's a ton of regularization methods. We're just covering some of the basic ones. And these basic ones typically do enough. Next slide.
All right. So now we're going to be talking a little bit about optimizers. So I can't really see the chat. So if you have any questions, if we drop it, and Edward will be answering questions in chat. But basically the gist of this is, how can we change attributes of our neural network, such as the weights and the learning rate, so that we can reduce the loss? And so as we can see, these are a couple optimization formulas that we're going to talk a little bit about each of these. So we talked a little about gradient descent in the last workshop. So we're going to start with batch gradient descent. This is also known as vanilla descent. So what this basically does is it computes the gradient of the cost function with regards to the parameters theta for the entire training set. And this doesn't really allow, okay, so the thing about this is we need to calculate the gradient for the whole data set every single time just to perform one update. So think about how slow that is. Think about a neural network, like in my background. To calculate each one of these, you have to go through every single one of these connections in order to update it just once. And this is really slow. This is intractable for data sets that don't really fit in your memory. And it doesn't allow us to update our model online. or on the fly because of how slow it is. And so, you know, this is the code for it. As you can see, each time you update in each epoch, you have to evaluate every single one of those connections. And there's a loop over the training examples that evaluates the gradient with regards for each example. And so how can we, you know, make this a little faster? Like, for example, how can we not consider every single one of these connections? So that's where this thing called mini batch gradient descent comes in. So what this does is, you know, we have a fixed number of training examples, which is less than the actual data set. So we're not looking at the entire data set every time we want to do an update. We're just looking at a mini batch. And so in each of our epochs, we pick a mini batch and we feed this mini batch to our neural network. And then we calculate the mean gradient of this mini batch. And we use this mean gradient to calculate, we use that mean gradient that we got in step 3 to update the weights. And, you know, we keep repeating these first 4 steps for each of these mini batches. And as you can hopefully, you know, kind of tell or imagine, this is going to be a lot faster because the average cost over the epochs in each mini batch gradient descent fluctuates. Well, you're not considering every single connection. And overall, the average cost of the epochs in each mini batch is going to fluctuate a little because, you know, we're averaging only a small number of examples each time. But overall, the entire system will run a lot faster. And this is like some code for a mini batch gradient descent. So as you can see in the beginning, you shuffle the data, just like randomizing it. And for example, this is a batch size of 50. And you just consider these 50 and use those to update your loss function rather than considering every single one. And so, yeah, so this is code for like a mini batch of size 50. But sometimes considering like an entire mini batch can still be, you know, a little slow. So how can we improve this even further? That's where stochastic gradient descent comes in. In stochastic gradient descent, we consider, instead of considering like a batch of examples, we just consider one example at a time. And so at each step, we don't take, you know, at each epoch, we just take one example. We feed this example to our neural network, and we calculate its gradient. And then we use this gradient from step 3 to update the weights. And you repeat these first 4 steps. And since we are, you know, just considering one example at a time, the cost will fluctuate a lot because, you know, it's not as accurate as, you know, considering an entire batch or the entire data set at one time. But in the long run, we will see that the cost will decrease because disregarding those fluctuations. And so this is some code for stochastic gradient descent. So as you can see, similar to in batch gradient descent, we start off by randomizing the data. So we shuffle them so we can choose a random point, but we just consider an example when we are upgrading our loss function. And we can kind of have a visual of how these past 3 optimizers kind of look in a graph. So Edward?
Yeah, so the main takeaway of this graph is that as the training set or the number of data samples that we get increases, the more, I would say, methodical the fashion is in which the neural network approaches the optima. As you can see, that batch gradient descent, which takes the whole input, it goes in like the most methodical manner, and the most kind of erratic manner, most erratic training comes in stochastic gradient descent, since it's basically training per data point. Yeah, and that's the mean. Because so I guess like what we wanted to like get this point across is that training and going to the minima is sort of like a roller coaster ride. And if you use like a batched gradient descent roller coaster ride, it would probably be the most smooth, and it'll just be like a downwards thing. But then if you do something like stochastic gradient descent, you're gonna like be like rocking around, like a really like janky roller coaster. Next slide.
All right. Do we have any questions? Okay, I guess we'll continue. So, you know, we consider those past 3 optimization methods and how can we improve upon stochastic gradient descent? And so we have this thing called, oh, by the way, Catherine wanted a shout out for stochastic gradient descent. So here's your shout out. But so how can we implement momentum to improve our stochastic gradient descent? So momentum, hopefully if you've learned about physics, you kind of know what momentum is. But in neural networks, momentum is like a method that helps accelerate the stochastic gradient descent in the relevant direction. And this helps dampen those oscillations. It does this by adding a fraction of the update vector of each of the past steps to the current update vector. And so you can kind of think of this kind of like a roller coaster too. So if you think about it as a roller coaster is, going down, as it keeps going down, because of gravity, it's going to keep going faster and faster. And so when it reaches like maybe when it's going back up, it starts to slow down because it's changing directions. And this is kind of similar with stochastic gradient descent when you implement momentum with it, as in that if it keeps going in the same direction, it's going to start moving faster and faster because it knows it's going in the right direction. We've been moving in this direction for a while. So we keep going faster until it changes directions. And then that's when it starts to slow down a little. And so you can see in this chart on the left where the red is without stochastic gradient, without momentum. And so as you can see, it's very, very janky. It keeps moving up and down. And it's a lot slower. But when you implement momentum, you can see that it sees it's going in the same direction. And so it starts taking bigger steps. And so it ends up having a lot less oscillations. So, what can we do to improve this even further? We can implement momentum and acceleration. So for example, if we think of it like a ball rolling down a hill, if it just blindly follows the slope, it's highly unsatisfactory, right? We want a smarter ball, a ball that has a notion of where it's going so that, it doesn't have to slow down. It doesn't have to wait till the hill slopes up again before it starts slowing down. So we use this thing called Nesterov accelerated gradient, also known NAG, which helps give our momentum this kind of prescience. So this gives us an approximation of the next position of the parameters, which is like a rough idea of where our parameters are going to be. So we can now effectively look ahead and calculate the gradient, not with regards to our current parameters. And so we can take a look at this this diagram on the left with the blue, the brown, and green arrows. So momentum, it would first compute the gradient, which is like that blue arrow, the smaller blue arrow. And then it takes a big jump in the direction of the updated accumulant gradient, which is that bigger blue arrow. And so, but with NAG, we're now looking at the brown arrow. So NAG first makes that big jump in the direction of the previous accumulated gradient, which is that first longer brown arrow. But then it measures the gradient, and then it makes a correction. So it goes back down a little bit, and that correction is that red arrow. And so if you've, I think it's in Math 20C or something, where you learn like adding vectors and stuff, you can see that the resultant vector is that green vector. And this anticipatory update prevents us from going too fast and results in increased responsiveness, which has significantly increased performances of neural networks. However, Edward wants me to mention that acceleration is rarely used in industry nowadays. So next up, we have AdaGrad. So this optimization adapts the learning rate to the parameters, and it performs smaller updates for parameters associated with frequently occurring features. And so larger updates for parameters and larger updates for parameters associated with infrequent features. So for this reason, it is a lot more well-suited for sparse data when data is like all spread out and stuff. And this is different from before where we had the same learning rate for each parameter. AdaGrad modifies the general learning rate at each time step for every parameter based on the past gradients that have been computed. And so one of AdaGrad's main benefits is that it eliminates the need to manually tune out the learning rates. Most implementations, they start off with a default value of 0.01 and then just leave it there. But the thing about AdaGrad is it's accumulation of the squared gradients, which you can see the GT in the square root at the bottom. Since every added term is positive because it's squared, the accumulated sum will keep growing during training because this is like the sum of all the squared gradients in the past. And so as this keeps increasing, you can kind of tell that the denominator will keep getting larger and larger. And eventually, the learning rate will keep shrinking because the denominator is increasing, and it'll eventually become infinitesimally small. And at this point, the algorithm is no longer able to acquire additional knowledge because, you know, there's no more learning rate. And this is kind of like a visual of what it looks like.
Yeah, so this visual is like a visual explanation of what Alvin just mentioned. We can see that the kind of like blue one is gradient descent, like just pure gradient descent without momentum or acceleration. And the white one is AdaGrad. And this kind of like makes sense because in the green one, it's like trying to find the local optima per point, whereas AdaGrad is taking into account previous gradients also. So with gradient descent, we can see that it's going to go first to the saddle point, which is quote unquote the lowest point at that particular instance, and then proceed to go even lower. Whereas AdaGrad essentially realizes that they can take a different direction and basically not go to the saddle point directly, and just go more directly toward the local or the minima.
Thank you, Edward. So next up, so we noticed that in AdaGrad, because of that denominator, eventually the learning rate goes towards 0. So, you know, how do we improve this? And that's where this optimization called AdaDelta comes in. And so AdaDelta is essentially an extension of AdaGrad, but it seeks to reduce that aggressive monotonically decreasing learning rate. So instead of accumulating all the past squared gradients, AdaDelta restricts the window of accumulated past gradients to some fixed size W. And so as you can see now in the denominator, we have an E surrounding the gradient, the sum of the gradients, and that helps make sure it doesn't get too large, because if it gets too large, the learning rate is going to eventually go to 0. And so instead of inefficiently storing W, previous squared gradients, the sum of these gradients is, you know, now recursively defined as a decaying average of all past gradients. And so this new running average depends only on a previous average and the current gradient. So this prevents the learning rate from, you know, going towards 0. And now we have something called RMS prop, right? So this kind of uses a combination of the gradient, the efficiency that we get from mini batches, and how we average all the mini batches, and it allows us to combine these gradients. And this overall, it dampens oscillations in a different way than momentum. So for example, in oscillations, when we point on a graph, it oscillates back and forth. Oscillations are when we point on a graph and it oscillates back and forth at specific gradients. And momentum dampens these oscillations by adding a fraction of the update vector of the past time step to the current update vector. And this adjusts the learning rate automatically and has a different one for each parameter. And this also automatically decreases the size of gradient steps so as not to overshoot this minima. And we have a visual of this. So Edward can talk about it a little more.
Yeah. So what this is basically showing is the methodology in which AdaGrad and RMS prop essentially calculate the local or the minima. I keep saying minima. So as we can see in the diagram, RMS prop seems to have less kind of like range in which it's evaluating all the values. We can see that using the little like corner gray thing, whereas AdaGrad has a much larger one. And what we could take away from this is that RMS prop is like looking at a smaller like potential sample space compared to AdaGrad for the direction of lowest descent. And that's like represented in the formula also.
Yeah, here's the formula. And something else to mention is, you know, we essentially want to keep moving this average of the squared gradients for each weight. And then we divide this gradient by the square root, the mean square, and then which we use this to adapt to the learning rate. And so you can kind of see this in the formulas on the left. But let's see, we're going to move on to ADAM. And ADAM is kind of like a combination of AdaDelta and AdaGrad. So this is a method that computes the adaptive learning rate for each parameter. And in addition to storing an exponentially decaying average of the past squared gradients like AdaDelta, ADAM also keeps an exponentially decaying average of the past gradients, which is similar to momentum. So this kind of combines the momentum and RMS prop. And what we can kind of think of this kind of like a roller coaster too. except imagine that this roller coaster now has like a lot of people on it. So this roller coaster is really heavy. And you can imagine that with really heavy roller coasters, there's a lot of friction. And although, you know, and so because, Edward, why are you laughing? Okay. And since it has so much friction, the faster it tries to go in a certain direction, the more there is a force pushing back against it. And so this kind of prevents it from, you know, going way too fast and stuff like that. And here we have a visual of that.
So this is like a visual of the most common optimization functions, and essentially like a picture of how they perform. So in the bottom, you can see like the number that's moving. That's the, like, I want to say the time steps that's happening. And also for each of these is graphing like how much time it takes for it to reach the minima. We can see that at a delta and RMS prop reach the minima the fastest, whereas gradient descent and momentum just get stuck in a local, I want to say that kind of like a local minima, as David like noticed earlier. And we can see that Atom, although it's not as fast as at a delta or RMS prop, the curve that Atom has is probably the most, I want to say the curviest, which kind of just means that it's able to get like a really good solution. Yeah.
All right, thank you. And so, man, I didn't do a poll for this one. Why don't we just drop our answers in chat? So, you know, what type of optimization algorithm, after learning about all these, do you think we should use for classification? Anyone in chat? No one has any guesses? All right, I'm just gonna go to the answer. So we can actually use any of these. And Edward, you want to take this one?
So go to the next slide, please.
Oh, wait, I forgot. Oops.
Yeah, so the basic takeaway is that, yeah, we can use any of the optimizers for finding the minima, but the only issue is that we want to find this the fastest and also the most accurately, because we can also notice that sometimes it takes like a really long time for it to find the minima, or sometimes gets stuck on a local minima, or somehow oscillates near the local minima and isn't able to just like get directly down to the lowest point. And as a result, and like through those diagrams that I showed you earlier, we can kind of see like this like being hashed out, where like some functions take longer to reach the local minima while others like start bouncing around near the local minima. And I guess the main takeaway is that each of these optimization algorithms is different, but generally Atom is the most optimal one because it has like the best balance of being fast and also accurate. So it's recommended to use Atom for most applications. Also, we can notice that we can use AdaGrad when there's only sparse data, since Alvin mentioned earlier in the formula, it's not as affected by sparse data or like not having enough data. And as a result, we can use AdaGrad for that. And also, and a similar kind of realization is that we can't use stochastic gradient descent really well for deep neural networks, because as we can see in those previous graphs, like the more complicated the function, the more likely it's going to get stuck at a local minima instead of reaching the global minima. And like a really important thing is that these optimizers are all based on backpropagation, which we talked about earlier, but there are other optimizers that aren't based on backpropagation, which are based on genetic algorithms, which we'll be covering in a later workshop. And also genetic algorithms are really fun.
Very cool. All right. So next up, we're going to move on to a very important question is like, how should we initialize our neural networks? And this is really important because how you initialize your neural networks is going to directly impact how your neural network learns at every single stage. And so it's very important to know how we initialize, very important how we initialize our neural networks. And first off, I'm going to start about how we should initialize our weights. And so we're going to first talk about what happens if we initialize our weights with 0. So during each of these connections, if we initialize our weights to 0, we can take a look at this formula or these equations in the bottom. you're going to notice that when weight or the W is 0, all the A's are going to become 0. And since and then the H's, the H1, H2, and H3, they're all equal too. And that means that during backpropagation, nothing is ever updated because all the weights are the same. And all the nodes in this hidden layer are learning with the same parameters with regards to the input. And this causes redundancy, and thus our neural network is never going to learn, right? And so what if we did it with a random value, but we use the same random value every single time, right? So it's not 0 anymore. And I decided to put in a random meme since we're talking about random stuff. But basically, in the end, this results in like a similar problem because all the weights when all the weights have the same value, all the units in the hidden layer are going to end up being the same as well. And if you take a look at this image, every single one of these nodes is affected by every single one of those arrows. And so if each of these weights were always the same, each hidden unit will get the exact same signal. And it's not going to update very well. And so what if we, next up, what if we initialize with just random values, right? Another random meme because we're talking about random values. But so we can initialize these weights with either a small random value or a large random value. And I'm going to talk a little about each of those. If these random values were started off small, we're going to encounter a gradient descent vanishing problem, which means that the gradient descent is going to eventually become 0. So basically, like after a couple of epochs, you'll notice that the variance is decreasing. This was like done through tests and stuff. We'll probably have code for it later. But you're going to notice that the gradients are saturating towards 0, which is known as the gradient vanishing problem. And so you can kind of visualize this as like each gradient is obtained as a result of a chain of multiplications of the derivative. And with each value, it's smaller than 1 because it's a small, you initialize it with a small weight. And thus the gradient vanishes to 0. And with the gradients becoming so small, your neural network is going to be really super inefficient. So what if we did it with like huge random values, right? So, but the thing is, if your values you initialize your weights as random large values, these values are going to explode because the weights are so large. And you're going to have the gradient saturation go towards 0 again. So you can kind of imagine this in the graph. As the neurons get saturated to extremes during the forward pass, and then we multiply these weights, it'll increase so fast that when you saturate it using, for example, sigmoid, the derivative eventually becomes 0, which brings us to the same issue as when we had small random values. So in this graph, you're going to notice that blue line is our sigmoid function and increases so fast that it reaches that limit really quickly, right? That limit of 1. And you're going to notice that that orange line, which is the derivative of this, eventually becomes 0 too. Like it becomes pretty big when it's increasing, but it increases so fast that it gets to that limit so really quickly, and it's back to 0 again. So to summarize this, if we initialize weights that are too large or too small, the gradient's going to go towards 0, because in both cases, when we initialize the weights as a small value or a large value, they vanish because in small values the gradient vanishes because of the repeated chain multiplication, and in with large random values, it vanishes because the derivative itself becomes 0. So both of these can't be used. So what can we use? And we're going to talk a little about the goat, Xavier. And he's not an actual goat, but he is the goat for coming up with this. And what we do is he came up with this way where you choose random distributed data bounded by this formula, the root 6 with the root n subscript I plus n subscript I plus 1. And using this formula, by initializing your weights using this formula, you maintain the variance of activations and backpropagated gradients all the way up and down the layers of networks. And this was developed by Xavier Glorot and Yasuo Bengio. And they came up with this way by setting the layers weights to these values bounded by this equation, this formula, where Ni is the number of incoming network connections. So like in my background, the number of all the lines going into a node. And then Ni plus 1 is the number of connections going out of it. So the ones going out of each node. And using this formula, it improves the efficiency of your overall learning rate by a lot. And let's see. So now that we talked a little about how to best initialize our weights, we're going to talk a little bit about how to best initialize our biases.
So generally, we can see that in the most used activation functions, the most significant change happens at 0. So as a result, we generally want to initialize our biases at 0, because then we can see when the neurons will be able to activate the most. However, there has been some articles that say that we should also, or we might initialize it to near 0 instead of 0, because as we can see in ReLU or TAN, if we initialize the bias to 0, it's literally not going to do anything, because in ReLU and TAN, they're both going to be 0. So sometimes you would also want to initialize it to near 0, like 0.01 or something like that. And now we're just going to look at, so the next one is just a resource to kind of show these optimizations for weights and biases. So Alvin, can you click on that link?
Yeah, I got you. I need to reshare though. I need to reshare my screen. I need to stop sharing real quick. Give me 1 sec. Chrome, where's Chrome? So we're gonna take a look at how each of these biases, these weight and bias initializations affect our learning rate in the long run. So I'm gonna share a screen, and it should be. Wait, which one is it? Oh, there we go. Does this work?
Yeah.
Can you
expand the page?
Like this?
Yeah.
Okay. So, Edward, you want to lead this one?
Okay. So this is basically like a visualization of the different initialization methods and what kind of happens when we do different initializations for weights. So as you can see, right now it's at 0, and even after training it for 100 epochs or something, the weight is still 0, because multiplying any value by 0 is just 0, so it doesn't do anything. And now when we do a value that's too small, when the value is too small, we can see that changes happen really slowly.
It'll take a while, yeah.
Yeah, it takes really long.
There we go. You can kind of see it starting to curve down.
Yeah.
So yeah, it happens really slowly. Now let's look at too large.
And now once it's too large, it's gonna just take way too long. It takes way too long for this one.
Wait, it's supposed to do something else. The heck?
No, just give it some time.
Okay.
It takes a really long time. It's massive.
My computer is overheating.
Oh, yeah, it takes a really long time.
All right, well, you guys get the point. It takes a really long time. Now, what if it were appropriate? So you can kind of see it's pretty steady. And this is a really good website for you to explore around. It's linked in the slides, but you can, mess around with different data sets. So for example, data sets that can, easily be split by a line, or data sets that are kind of sparse, or data sets where it's surrounded like this. And you can kind of explore how what happens when you initialize your weights differently with too small, too large, or 0, and compare that with when it's appropriate. So is there anything else you want to add with this, or anything else you wanted to show with this?
I think that's good.
Okay. And now we'll be looking at some code. So Edward, do you want to share screen for that, or do you still want me to continue sharing?
Yeah, can you continue? Let me just find the code right now.
Are you going to share?
Yeah. Okay, I'll share this one. Yeah. Okay. Can you guys see the GitHub page?
Yeah.
Okay. So what this is basically, this is just a demonstration of different optimizers using TensorFlow. TensorFlow is a really good package that we will talk about more in depth later on. But TensorFlow does like a lot of the stuff that is like really complicated. Like creating a neural network requires like a lot of math and stuff like that. And TensorFlow can just like create this whole giant neural network for us. Like we can see here, this is just like a dense layer of size, a two neuron net layer, and this is like a 64, and it allows us to do backprop and all of those calculations like automatically. And we can see above, these are the optimizers: SJD, Atom, AdaDelta, and RMS prop. So like how to implement, or just how to call one is just to do TF keras optimizers, and you can get the optimizer. Yeah, and I think if you run this code, you'll be able to see that RMS prop Atom performs the most well on this data set. This is just like a simple demonstration of MSE trained using a neural network. And yeah, and then we can also see that SJD is doing the worst. Yeah, and then we also have some code for regularization. Yeah, so regularization is just basically how the initialized variables are going to be regularized. And can you expand on this?
Oh, okay. I was going to tell you to talk about the neural network modeling competition. But if you scroll up, go to like line 20-ish. Sorry, go to line 21, 24. So what we're doing here to demonstrate regularization is our training data is trained on a data set from the range -1 to 1. So the function we're trying to model here, I think, is just sine of x. And the thing we want to generalize it to is to the range -3, 3, which is very difficult if you don't have regularization. So if you run this code, you see that with regularization and without, you see there's a bit of a difference in loss. It's not perfect, but when you don't have regularization, the loss is much higher than with regularization. And in the future, we're going to have a neural network modeling competition for you guys to apply your skills you've learned through our workshops, where we're going to give you a data set full of input values and output values, and you're going to try to guess what the function is using a neural network and predict on a wider range, as an example. Can you scroll down? So the way we create a regularized neural network, as an example, is here in TensorFlow. We would have the same thing as usual, but what we do is we add a thing called kernel regularizer, and you can pass in what's known as a regularizers.l2, which is what we talked about today. So regularizers is inside tf.keras.regularizers. I pulled it out, and you can pass in the regularization parameter. Now you might ask, like, why isn't this not included into the loss function? Because as I showed before, we actually add the regularized loss directly to the loss function. That's because when we're doing the update step, it's really simple. The update step when you're adding regularization is actually just adding, I think it's a constant value to each layer. So like on each layer when updating all the weights and biases update the same way regardless of whether or not there's regularization. And we do some of the math, the way weights update is just only slightly changed. That's dependent on learning it. And what's known as a regularization parameter. In this case, we use 0.01.
Yeah. So this is kind of important for our neural network modeling competition, because for the competition, we're only going to provide you with like a subset of all of the data. So let's say, as Stone mentioned before, like let's say we give you like data from -1 to 1, but we're going to test it on something from like -1.5 to 1.5. And what this basically is doing is that it wants to see how well your function is able to generalize to like unseen data. Because with different tasks such as classification, this is like a really important thing to like be able to generalize, but it's not as well visualized or explained using classification, because in classification, the pattern in the data is much harder, or like way harder than like a function that you can like simply visualize using like a 3-dimensional graph. Yeah. So now, after you looked at the code, can you guys respond? Oh, we have like a survey form at the end to gauge like interest and how we can improve future workshops. So yeah, like, thanks for coming. So if like you can respond to that, that would be nice. And there's the meme. Yeah, thanks for coming.
Whoa. Thanks, Edward.
And resources. And I think this was made on TensorFlow 2.0. So you probably should do that because TensorFlow 2.0 and TensorFlow 1 are different. Yeah.
I can finally see the chat. Let's go. Oh yeah, if anyone has any questions, feel free to drop them in chat.